That ability to eliminate the stuff and only focus on what you need is very, very essential to geometry in general, but in the ACT in particular. They like to occasionally just throw a problem at you that's got way too much information. And your brain can leap to, oh, I can do this and this and this and this, but you only need the little piece. And so despite what we're going to do today, I want you to keep that in mind for the test overall. Don't overcomplicate it. All right, so we have a right triangle. "30 degrees, 20 meters, and they want the length in meters of this side. But it is an exact answer, not a decimal. All right, either online or in person. If you have an answer, raise your hand. Okay. If I say special right triangle, does that trigger anything in the depths of your brain? It's been a while since geometry. All right, so 30, 60, 90 triangles are one of the special right triangles. I like to teach them as half of an equilateral triangle. Because in an equilateral triangle, all the angles are 60, all the sides are the same. And that's where this comes from. If we take half of this and call it x, then this is also x, and the longest side is double this, 2x. If we run the Pythagorean theorem with the x's, you will end up with 4x squared, and then subtract the x squared, and you have just the square root of 3x to be your leftovers. And so this is x times the square root of 3, is that third side within this special right triangle relationship. So if this is 20, down here is only 10, and this is going to be, the x is getting confusing, so we'll just say this is 2y, this is y, this is y, square roots of 3. We replace y with 10. And so it is 10 square roots of 3 for our length. If you ever get a problem where they give you this side and say, I don't know, this is 5, you're going to solve that y square roots of 3 equals 5, and then find out what that side is. And so the relationship stays the same always, it just depends on where you start with it. So So I believe these are on page 4 at the top if you're using that math note packet, but that's what we're working with. All right, so the second one, same sort of category, we're talking about the special right triangles again, says that the diagonal of a square is 18 inches. And the question is, what is the side length of that tile? If you've done unit circle stuff in Algebra 2 recently, this likes special right triangles a lot. So this is the pattern that you memorize the x square roots of 2. This is kind of derived from that, as if you start with this side instead, that's what you'll end up with. But you could very well start by solving 18 is equal to the square root of 2. So x equals 18 divided by the square root of 2, rationalizing the root. You end up with 18 square roots of 2 over 2, which equals 9 square roots of 2. So again, this one again is easier to rederive if you happen to not remember. You can know that these are the same, and so you can solve that x squared plus x squared is equal to 18 squared and go back that route if you don't remember. The 30, 60, 90 is harder to rederive if you don't remember it, but this one is pretty straightforward. If you don't remember the pattern, as long as you know the sides are the same, you can still Pythagorean theorem it. Again, they introduced this as half a square. Half a square, equilateral triangles. Also, if you have a hexagon, a regular hexagon, you might see this because these are going to be the same. It's the altitude, that sort of thing. And so that's where you will see those special right triangles show up. All right. So I'm going to give you a lot of words, but just draw the picture. It says that a playground slide is 10 feet long, and the base of the slide is 8 feet from the base of the ladder. What is the height in feet of the ladder? you're running the Pythagorean theorem, you're missing time. It is 6. Again, Pythagorean triple, 3, 4, 5, 8, and 10. This is going to be 6. It's just double that 3, 4, 5. Again, if you haven't gotten it from me yet, please memorize 3, 4, 5. It shows up all the time. They really, 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 really like it. So, not hard, just there. Okay. So the next section that I'm going to focus on is area. And I'm mixing up the two groups. Have I talked to you about the area of trapezoids yet? That's a blank stare, so I'm going to go with no. So, we're going to start with square. We're going to have rectangle. We're going to have parallelogram. We are going to have triangle. And we're going to have trapezoid. How many of those formulas can you remember? If you were asked to find the area of any of these shapes, how many can you remember? All right, no shame in saying, yeah, I didn't remember this one. It's been a while. For a lot of you, you've been doing upper level math for several years, and sometimes the formulas get lost. Is there any that you need a refresher on? Okay, so my quick rundown is that square is literally the side squared. That's where squared comes from. This one will be length times width. This one is a variation of that because you can chop off this triangle and put it over here. It's still the same amount of area. And so this is the side of the length times the height. The triangle is literally half of the rectangle. So it's the base times the height and divided in half or divided by 2. The trapezoid is defined as base 1 and base 2. It doesn't matter which is which. It's just talking about the two parallel sides. We're going to average them together because that is this middle right here. We're taking the average of those two by adding them together and dividing by 2. And then if we chop off this corner, we can put it up here. Chop off this corner, put it up here, we can still turn it into a rectangle. And so it's this average of the two bases, or the middle of those two bases is base 1 plus base 2 divided by 2. And then again, we multiply it by our height. So those are formulas that you will be expected to know. Other ones that you might see not as common, if you have a kite, how would you find that area? Again, it's just half of a rectangle. And so it's this diagonal multiplied by this diagonal. And then diagonal 1 times diagonal 2 divided by 2. And so the more you can remember how it relates back to the rectangle, the easier the formulas get. So, again, the ACT walks a fine balance. It wants to be accessible to everyone who has had the standard high school education, and so they are not trying to throw calculus at people who have not taken calculus. But at the same time, they want to be tricky. They want to be difficult. They want to separate out, oh, these students are particularly good at math versus these ones passed the class and did okay. And so, in the light of that, trapezoids are one of their favorite shapes. They're going to throw it at you some way. So, the first thing is we have a trapezoid. We have a 5 up at the top, we have a 19 down at the bottom, we have x, and we have x. They're the same on both sides, and we're told that the perimeter equals 48. What is x? Okay, I agree. So 5 and 19 together make 24, and then subtract, we still have 24, share it equally between the two sides, x equals 12. So, follow-up question, what is the area of this trapezoid? I'm going to give you a full minute on this one because it's got some trickiness to it. Go ahead and leave your answer as an exact answer, not a decimal. All right. So this one is only possible because these are the same. If they were two different lengths, this is not possible, but because they are the same, we can take this chunk right out of the middle, obviously not drawn to scale, but this would be 5. How long would this piece be? And we already worked out what these were, so we need to use that 12. Only one side's necessary, I'm just writing it on both. But what next? Pythagorean theorem, we've got to figure out what our height is. And so, what did you end up getting? Square root of 95. And so, that, if we take 5 plus 19, that was the 24, and then dividing it, it happens to work out to 12 again. That's not necessarily the case, it's just the way it happened. And so we would have 12 times the square root of 95. And so within these trapezoids, because they have a set of parallel lines, because they have these different abilities within them, they can be kind of a creative problem. And so the ACT likes trapezoids. All right. One more. What is the area of the triangle?
What is it asking again?
What is the area of this triangle?
Like as a whole, the solid line, or like the dotted one?
The solid one.
Okay.
The dotted exists just to be able to give that distance.
Okay, thank you.
Okay, so should be a relatively quick thing. This is just a check-in to double check that you know. The area of the triangle as 1/2 base times height still works even if the height is not touching that triangle. And so this is literally just 1/2 base times height. For me, it's easiest to say, okay, 1/2 of the height is 2. 2 times 7 is 14. And so it would be 14 units squared. There's a mathematical proof on why that is, but that's not ACT. If you ever want to talk about it, I think it's fun. All right. So, we're getting into perimeter now. In general, I don't have a whole lot of concern about perimeter, but this question in particular is very ACT-esque. It just ticks all the boxes of things that they like to throw on the ACT. So it is 12.5 across the bottom. It is 10 meters tall. And they tell us that this valley is 7.5 meters deep. What is the perimeter of the shape? Sorry for the rattle. So, intermediate question, if it didn't have that valley cut into it, what would the perimeter of the rectangle be? It'd just be 10 and 10, or 2 10s, and then 12.5 and 12.5, or 2 12.5s. And so that's essentially moving this piece up to here. The only thing left of the perimeter is 7.5 and 7.5, or 2 7.5s. And so getting comfortable with the idea of, oh, I could just rearrange the sides. These are the lengths that I need. This is what's going on. That one is something that I want you to be comfortable with. Am I hand waving too much? Am I stating the obvious in your board? You're doing a really good impersonation of crickets. All right. For the area of a square to triple, the area of the square is multiplied by 3. The new side lengths, we're going to use n for new, must be the old side lengths. Yeah, we can't use O. We'll just use S for side. Multiplied by what? In order for the area to triple, what do we need to multiply the sides by? If you're done with that first one, or if you're feeling stuck on that first one, go ahead and give the second one a try. So, if this question is too conceptual for you, you get to pick your numbers because it's going to be a constant either way. And so I would say that the area of the square triples, okay, the original area, I'm going to make 1, and the new area, I'm going to make 3. Because this is 3 times as big, right? This comes from our side times our side. And this comes from our new side times our new side. And so the area of this square is s squared. Our area of our new square is n squared. And we're told that the new one is 3 times as big as the old one. And so, in order to make 1, S is just 1. 1 times 1. 1 squared is just 1. And so, what's the length of the new side? Square root. N is equal to the square root of 3. second one, slightly easier, but same concept, and then we're gonna talk about the two of them together. So, the original, or the small triangle, has a side length of 4 and an area of 8 units squared. This adds on 12 more. What would the area of the large triangle be? So, what's going on is, if we consider this entire thing, how long is that side? 16. And so how does the length of side compare to the original length of side?
Double.
More than double. We started with 4 and we ended up at 16.
Oh, we're talking about before.
Yeah. So from the little triangle to the big triangle,
Quadruple.
we quadrupled, we multiplied by 4. So the key that I need you to know in order to do this problem is that area does not quadruple. Area does not multiply by 4. Because if we think about it, if we have a block of size 1, if the area quadruples, all we have to do is multiply it in one direction, and this becomes 1 times 4. If the length quadruples in both directions, and so we also have 4 in this direction. What's 4 times 4? 16. And so the area is going to be 16 times as big. And so if our scale factor is f, and the factor is 4, the area scale factor is going to be 4 squared. And if we talk about the volume scale factor, if we're talking about a cube or some other volume, if we scale the volume would have been 4 to the 3rd power. And so scale factor, it's just about the lengths. But if we're talking about area or volume, we need to square or cube that area or volume. And so it doesn't just grow in one direction, because that would be multiplying by 4. It grows in both, and we have to multiply by 4 times 4, or whatever the scale factor is. And so that's why when we changed the area by 3, the length was only by the square root of 3. It was the work backwards from that, but that's kind of hard to see. All right. So we're told that a table has a diameter of 6 feet. But we are also told that on the scale, 3/4 of an inch equals 9 feet. And so the question is, what is the area in square inches on the drawing? So, oh, it should have been 3/4 inches. Sorry, I forgot to copy that part. So, 3/4 inches is equal to 9 feet. What would be the area of the drawing of the table? again, leave your answer in terms of pi unless told otherwise. So the first thing that I'm curious about is how do you go about finding the radius of the drawing? How do you get from this to work with the 6 feet to get a radius so you can work with area? U divided by 2. Okay, so you went to the idea that this is 3 feet. But how do you get from here to here? There's no right answer. I'm just curious how your brain is working. The two ways that I see it are to either set up the proportional fraction cross multiply or just instinctually see, oh, 3/4 inches is 9 feet, so 1/4 inch is equal to 3 feet. And so I kind of just convert the scale in my brain. And so if you see that, great. If you don't, you're looking at 3/4 over 9 is equal to x over, you can either find the 6 or the 3, either one would work. If you use the 6, you'd have to cut it in half after you find x. If you already use the 3, then you're just finding your radius. And so both of those are okay. But if you can see it, great. I was just curious how people were tackling that. So this ends up being 1/4. And what do we get for the actual area?
1/16 pi.
Yeah, because 1/4 times 1/4 is 1/16, and then pi. All right. At first glance, I thought this was tricky. I'm not sure if I'm going to see a shortcut once I begin, but we have an equilateral triangle, all sides being the same, of A, B, and C. And inscribed inside of it is a square, despite my drawing. And the area of this square is 12 units squared. And the question is, what is the perimeter of triangle ABC? intermediate step, what is the length of a side of the square? So because it's a square, our sides are the same. So s squared is equal to 12. S equals the square root of 12. This factors out as square root of 4, square root of 3, and we have 2 square roots of 3. So we have 2 square roots of 3 here, but also 2 square roots of 3 here. Do you guys know where to go from there? Again, we were told that it was an equilateral triangle and the square was inscribed, or as you can see, touching the corners inside of it. With an equilateral triangle, it is going to be 60, 60, and 60 degrees. And because this being a right angle from the square, this is 30. And so it becomes a 30, 60, 90 triangle. If this length is 2 square roots of 3, our short length is only this. And so we have a 2, we have another 2. Again, with those special right triangles, if this is 2, this is 4. And so is this. If this is 2 square roots of 3, then this is also 2 square roots of 3. But more importantly, these are also 60 degrees. And so this is also 2 square roots of 3. This is also 2 square roots of 3. And so now we've got all of our pieces. We've got 1, 2, 3, 2 square roots of 3. And so we have 6 square roots of 3. We have 2, 2, 4, and 4. We have 12 units. And so it is 12 plus 6 square roots of 3. Probably the most difficult geometry problem I've seen. Not terrible, just a lot of pieces to it. A lot's going on with this one. So, again, you're kind of quiet feedback. Did I jump in too early with the answer, or was that about right? Okay. I would expect any one of those pieces to be fair game on the test, but if they put them all together, that would definitely be a last 3 question problem. All right, got time for one more. So we have a semicircle. My art skills aside, that's half a circle. And it has a radius of r inches. And a chord, so WX is the diameter, and there's a chord that is parallel to that diameter from point Y to point Z. So these are parallel. They don't put that on the drawing, but since we're cutting down on words, we'll mark it. So the length of YZ is 25% shorter. Than the diameter from W to X. So they ask us to find what is the shortest distance between the two chords in terms of R. So they don't give us that on the drawing, but it's kind of fundamental to solving this. So as far as what I mean the shortest distance, do you remember how to find the shortest distance between two lines? What is going to be special about the shortest distance between those two? They're perpendicular, and so we are going to be dealing with a right angle. Give you a couple minutes work, but we'll have to pack up soon, so. I drew it over here, but the first key to this problem is to put it in the middle. And the second key to this problem is to know that we can put the radius making a right triangle. The next is this relationship. If it's 25% shorter than WX, then YZ is equal to 0.75 WX. It's 3/4. But not just that, if this radius is half of the diameter, this is going to be 0.75 radii. It's going to be that same scale factor. And now it's just a Pythagorean theorem problem. If you wanted to be creative, I would actually plug in 4 and 3 there, and then it's just going to be that times R. Because once you're making the comparison, it works. But for consistency, we should probably stick with the originals. Anybody disagree with my math? Did I lose anybody? We have 1r squared minus 3/4 r squared. We end up with, so 16 minus 9 is where I got the 7 from, so we had 7/16 r squared. The r is a perfect square, 16 perfect square, square root of 7 gets left in the radical. Again, a lot of pieces that you might see, not frequently at this level of difficulty, but the ability to swing the radius down and make right triangles shows up all over the place with circles. And so that skill in particular, just remember, the radius is the same all the way around the circle. You can move it and make a triangle. And that comes up pretty much on every ACT test, something to do with the circle and the radius in a right triangle. So that's what I'd be aware of. The variable base, that one's a little bit more challenging than usual. But that is our preview of some of the trickiest ACT geometry stuff. I will be back at the beginning of April, and I'm not sure what I'm doing yet, so I can't tell you, but I can tell you, in general, if you send a picture in WhatsApp, and I will do my best to explain anything that you come across, so do not hesitate to ask.